Mesons, 1934 to 1947. Now there is one conspicuous problem to which the classical model does not address itself at all. What holds the nucleus together? After all, the positively charged protons should repel one another violently, packed together as they are in such close proximity. Evidently, there must be some other force more powerful than the force of electrical repulsion that binds the protons and neutrons together. Physicists of that less imaginative age called it simply the strong force. But if there exists such a potent force in nature, why don't we notice it in everyday life? The fact is that virtually every force we experience directly, from the contraction of a muscle to the explosion of dynamite, is electromagnetic in origin. The only exception outside a nuclear reactor or an atomic bomb is gravity. The answer must be that, powerful though it is, the strong force is of very short range. The range of a force is like the arm's reach of a boxer. Beyond that distance, its influence falls off rapidly to zero. Gravitational and electromagnetic forces have infinite range, but the range of the strong force is about the size of the nucleus itself. It is a bit of an oversimplification. Typically, the forces go like e to the power minus r by a divided by r square, where a is the range. For Coulomb's law and Newton's law of universal gravitation, a equal infinite. For the strong force, a is about 10 to the power minus 13 centimeter, 1 Fermi. The first significant theory of the strong force was proposed by Yukawa in 1934. Yukawa assumed that the proton and neutron are attracted to one another by some sort of field, just as the electron is attracted to the nucleus by an electric field and the moon to the earth by a gravitational field. This field should properly be quantized, and Yukawa asked the question, what must be the properties of its quantum? The particle, analogous to the photon, whose exchange would account for the known features of the strong force. For example, the short range of the force indicated that the mediator would be rather heavy. Yukawa calculated that its mass should be nearly 300 times that of the electron, or about a sixth the mass of a proton. See problem 1.2. Because it fell between the electron and the proton, Yukawa's particle came to be known as the meson, meaning middle weight. In the same spirit, the electron is called a lepton, lightweight, whereas the proton and neutron are baryons, heavyweight. Now, Yukawa knew that no such particle had ever been observed in the laboratory, and he therefore assumed his theory was wrong. But at the time, a number of systemic studies of cosmic rays were in progress, and in 1937, two separate groups, Anderson and Niedermeyer on the west coast and Street and Stevenson on the east, had identified particles matching Yukawa's description. Indeed, the cosmic rays with which you are being bombarded every few seconds as you read, this consists primarily of just such middleweight particles. For a while, everything seemed to be in order, but as more detailed studies of the cosmic ray particles were undertaken, disturbing discrepancies began to appear. They had the wrong lifetime and they seemed to be significantly lighter than Yukawa had predicted. Worse still, different mass measurements were not consistent with one another. In 1946, after a period in which physicists were engaged in a less savory business, decisive experiments were carried out in Rome demonstrating that the cosmic ray particles interacted very weakly with atomic nuclei. If this was really Yukawa's meson, the transmitter of the strong force, the interaction should have been dramatic. The puzzle was finally resolved in 1947 when Powell and his co-workers at Bristol discovered that there are actually two middleweight particles in cosmic rays, which they called pi or pion and mu or muon. Marshak reached the same conclusion simultaneously on theoretical grounds. The true Yukawa meson is the pi. It is produced copiously in the upper atmosphere but ordinarily disintegrates long before reaching the ground. See problem 3.4. Powell's group exposed their photographic emulsions on mountain tops. See figure 1.4. Figure 1.4. One of Powell's earliest pictures showing the track of a pion in a photographic emulsion exposed to cosmic rays at high altitude. The pion entering from the left decays into a muon and a neutrino. The latter is electrically neutral and leaves no track. Reprinted by permission from C.F. Powell, P.H. Fowler and D.H. Perkins. The Study of Elementary Particles by the Photographic Method. New York, Pergamon 1959. First published in Nature 159, 694, 1947. One of the decay products is the lighter and longer lived mu, and it is primarily muons that one observes at sea level. In the search for Yukawa's meson, then, the muon was simply an impostor, having nothing whatever to do with the strong interactions. In fact, it behaves in every way like a heavier version of the electron and properly belongs in the lepton family, though some people to this day call it the mu meson by force of habit.